I'm just going to go over basically a technical overview. So like, what is this technology? You know, how does it tick? And then I'm going to jump into kind of like why it matters. So why should you care about it? Like, why is it different than just the internet or anything else? And then I'm going to talk about some business models and some value creation, some value capture. So just where are people kind of looking at the blockchain technology stack as to how they can kind of build products and solutions that actually kind of sustain businesses. So let's jump right in with the technology overview. So basically, the blockchain is this distributed, transactional, immutable database and protocol. So that's a lot to chew on, but basically it is a database that's shared by everybody. It's transactional, which means updates form transaction records. So it's like if you've ever looked at Apache Kafka, it's kind of like that. It's immutable. So basically once you've updated sort of data entry like in the database, basically you can't go back and say that it never equaled what it equaled before. It's always moving forward. So that's done through Merkle computing. But basically, that's a computer science topic a little bit beyond today. And basically, at the core, it's a database and a protocol. So how is it secured? Well, how are all people trading, Bitcoin and Ethereum and stuff? And how are they putting their faith in this database? Well, it's secured by mathematics, game theory, and cryptography. And so basically, there's a complicated sort of way to update the database, which I'm going to walk through step by step in the next slide. But this is kind of what secures people's faith and people's belief in the fact that this database has no central owner, no central authority. You're not going to the bank of Bitcoin to kind of update your account and credit your account and debit somebody else's account. It's all in the protocol. And the protocol is secured by math, game theory, cryptography. People are incentivized to keep this whole Bitcoin and Ethereum and basically keep the blockchain secure. So these transactions that people make, they're placed in blocks, and the reason why it's kind of based on blocks is because it helps make time and verification trustless. So you put a bunch of transactions in a block, you don't need to really concern yourself with whether somebody's computer is timed perfectly with your computer. You basically know that if these transactions fit into this block and that block was verified by the entire network, then we can now trust that block, and then blocks that come after it happen forward in time. So the block kind of concept is like kind of trying to get away from timing everything. So Bitcoin has 10-minute blocks and Ethereum has like 2.5-second blocks or something. There's a bit of different architecture choices there. So verification of these blocks, it's incentivized. So it's open to anyone. Anyone can download a Bitcoin client or an Ethereum client and go ahead and start trying to verify blocks. And you're incentivized to do so by a thing called a block reward. I'll get into it a little bit more in the next slide. But it's really important to know that it's also Byzantine fault tolerant. So there's this problem with distributed computing that came up, I think, in the 80s called the Byzantine generals problem. And basically, if a bunch of generals surround a city and they're deciding to invade the city, let's say there's 9 generals, and 4 of them rush in and 5 of them want to retreat, then those 4 are pretty much toast. So what you're trying to do is you're trying to get all the generals to agree. So that the entire network is sort of believing in the next sort of updated state of the database. So that's kind of brought up a lot in blockchain sort of literature and in these white papers and stuff. So the important thing is that finalized blocks, the last step with the blockchain is finalized blocks are signed and connected permanently to the blockchain, and that's illustrated in this picture here. So what you do is you hash all of the data in the block that you're currently in, and you save that hash in the block that came before it, and you form a chain, right? So this is sort of through a cryptographic hash, and basically that keeps the database secure. So let's walk through the life cycle of a transaction. So again, I will be touching on some stuff, like I'm not going to go down the mining rabbit hole or anything like, or Merkle computing and tell you like how it's all kind of stored efficiently, but it basically is a transactional database. So we started with, block 0, no accounts, nothing. And then we basically started to issue transactions like create account, send Bitcoin, receive, right? Basically just send, and then the other person just gets it. You can't stop it from coming into your account. Basically, this is the transaction lifecycle. So some user will create a transaction, and then a node in the network will pool it into a block. So they'll take a bunch of transactions that are in their memory, and they'll basically say, okay, I think these transactions fill a block. Now I'm going to start to work on that block, and I'm going to broadcast that to the network so everyone else can start to work on it too. And then there's this thing where the network achieves consensus. So who is randomly selected as the main sort of winner of the block? And this is mining, this is related to Bitcoin and getting, earning new Bitcoins that are minted. I won't really go into kind of like how the algorithm works, but basically there's some consensus among the network as to who sort of is the main verifier of this block. They're going to win a reward, and then they're going to sign and they're going to chain it to the other blocks. And that means that the state of the database is now updated, and confirmations are just more blocks being put on top of the block that was just mined. So if you've ever heard somebody say, I'm going to wait for 2 confirmations, that means that 2 additional block rewards were given out, and these blocks were finalized across the network, and the whole network agreed this is the new state. So that's 2 confirmations. Typically for a high value purchase in Bitcoin, you'd wait for 6. And it's because, with every confirmation, the work that needs to be done to undo and to verify new blocks for the entire network gets exponentially greater. So that's why higher value transactions, you probably want to wait a little bit longer. But let's shift gears a bit, and let's talk about I'm going to transition a bit more into talking about smart contracts. So this is from Nick Szabo in 1994. So he's one of these cypherpunks, these guys that tried to create digital cash back in the day. And basically, Nick Szabo is trying to take a lot of subjective and sort of kind of like wet kind of transactions that we have in our world, like property and like legal accounting, audits, and things like that. These are subjective. You need to bring humans into the room. You need to pore over invoices. You need to look over kind of legalese. It can be interpreted in different ways. So this is what he calls kind of like this is wet kind of transaction software. This is subjective kind of stuff. He wants to, his vision is to kind of turn this into dry software-based code. So code is law. Basically, you enter into an agreement. It's right there in the code, maybe through some really awesome UX. It's communicated in a very straightforward way. Me and Igor could enter into an agreement to own something together on our phones just by kind of tapping a few times. And everything is executed by the software, by the code. So that's kind of like the vision for smart contracts. So let's take a look at the Ethereum blockchain. And these smart contracts actually exist today in a very basic form, but they are out there. So there's code being written in a language called Solidity. There's other languages. Solidity is more JavaScript based. There's other languages that look more like Python or Lua. But basically it's compiled into bytecode, and it's stored on the blockchain. So anyone can go verify that the hash of that bytecode and everything is all secure. And if you're entering into a smart contract agreement, you know that it hasn't been tampered with. Because again, the blockchain, it's immutable. At some point, somebody stored that code there, and that is in fact the contract you're entering into. Nobody can kind of swap it out on you. So it's stored on the Ethereum blockchain as a contract account. and this is a different account than like a wallet account. That's called an externally owned account, or an EOA. But smart contracts are stored as a contract account, and they're like a wallet account, but they're governed by the code that was originally stored. So these contracts, they have a key value database themselves. So they have a storage root that they start their state out at, at whatever they were initialized to. And then basically, they get updated by transactions. So you make a transaction to a smart contract by calling functions. It's very wordy on these slides, guys, so I apologize, but we'll get into some fun stuff to take a breather from the technical. But basically, computational steps in Ethereum are charged in units of gas. So this is not a different monetary unit than Ether or ETH. It's the same settlement currency, ETH. You pay for gas, you pay for computational steps when you call a function of a smart contract. And the reason why you need to pay per computational step is because the Ethereum virtual machine, they toss around the phrase Turing complete, and it's not really Turing complete. It just basically has a gas limit. So if you were to let some smart contract out onto the Ethereum blockchain and it had an infinite loop in it, what would that do to the 40, 50,000 computers that are running the Ethereum virtual machine? It would brick the whole thing, right? Uh-oh, all these computers are halted on this piece of code, right? So that's where they came up with gas. They basically just said, okay, we're going to make people pay for every operation. We're going to make storage expensive because, again, the database is transactional and immutable. So if we make storage cheap, everybody's just going to start shoving cat images on the Ethereum blockchain and it's going to get super big, right? So they make storage cost something, and they have every computational step, even in a for loop. So every time you kind of churn through a for loop, you're costing gas. And basically there's an upper gas limit. I think right now it's 6.5 million. It's always kind of increasing just, as the rate of computers just get faster and faster. So that's a bit about how it works. These tokens that everybody are issuing, if you see an ERC20 token, or people say, we are an Ethereum token, basically what that means is they are a smart contract on the Ethereum blockchain that represents a ledger, kind of like the main chain has accounts and balances. This is a smart contract on Ethereum, so it's a contract account that maintains accounts and balances. So it's kind of like ledgers on ledgers. So that's enough for the technical.